Pim, are you going to say a few words at the beginning, or should I introduce myself?
Okay, yes, let me do that. Hello, everyone. It's very nice to see you all back here. I'm very excited that now we're going to go into the meat, the real business of our course on category theory for AI. Today we have Petar Veličković talking about the fundamentals and the essential building blocks of categories.
Wonderful. Thank you so much, Pim, for the introduction. And thank you all for coming to the second lecture of our Cats for AI course. As mentioned, my name is Petar Veličković, and I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today I'm going to try my best to take the initial momentum that we kicked off from Bruno's great introductory lecture on the foundational reasons on why we should care about category theory as deep learning researchers, and maybe also for the mathematicians in the audience, why they should look into some interesting applications of this work to deep learning. And what we're going to try to do today is try to then take this motivation and build a set of guiding principles and essential building blocks that we're going to be using, well, not just throughout this course, but when you choose to apply these techniques in a downstream problem, some interesting ways in which you might be able to do that. So we're going to be talking about the essential building blocks, both of category theory and of the subsequent lectures. And specifically, we're going to try to build a better understanding of categories and functors. Those are our main objects that we're going to be studying today. There will be more objects of interest like adjoints, natural transformations, and so on. Those will be studied in the following weeks rather than the lecture today. Okay. So before we dive into the meat, as Pim put it, we are going to just start with a little bit of a recap. It's basically taking some of the key ideas that Bruno conveyed in his talk last week, and maybe I'll try to give a bit of a personal feel for those aspects. So why are we all here? And I trust that many people in the audience have had a chance to either see some slide deck or some paper or some talk that I have given in the past. And for those of you who know me before, you will likely know by now that I usually like to give talks about technologies that I am so passionate about that I'm confident that in the future we might all want to use them. And as you probably know, it all started with graph neural networks. I've been seen in many cases, both in person and virtually, kind of trying to pitch the story about how everything is a graph structure and we should be accordingly tweaking our architectures to exploit that graph structure. Then after that, we also took a very deep dive into geometric wonderland, and a product of this is our geometric deep learning text, together with Michael Bronstein, John Bruna, and Taco Cohen, which we are currently trying to finish up writing and will be hopefully a fully fledged book with MIT Press next year. Here you can see just one of the many illustrations that are going to feature in the book. You can see here Alice falling down the rabbit hole and into geometric wonderland. This is one possible imagination of what our book cover is going to look like. And as you might know, geometric deep learning, which Pim will tell you a lot more about in his lecture 2 weeks from now, is giving us the foundation of how we can build machine learning systems that respect the symmetries in real world data. So it's really all about a symmetry-centric approach. And therefore, we can use it to not only explain away all of the architectures in use in deep learning today, but also it can offer us a way to come up with new architectures for new kinds of interesting exotic objects with exotic symmetries that we might encounter in the future. And I actually see category theory as a natural continuation of this entire line of work. So category theory can, and you will see this in the following lectures, can be seen as a very clear generalization of many of the ideas in geometric deep learning, and therefore it can help us build architectures not only captured by the geometric blueprint, but also going beyond geometric blueprint into the realm of what we will talk about as naturality. So much like all of my co-organizers, Pim, Andrew, Joao, and Bruno, I also believe in a future where if you're a deep learning expert, you will probably find it useful to study some set of category theory foundations. And, it is our hope that these lectures will serve as a good foundation for something like that. So with that in mind, what will we actually do today compared to last week? Well, we will talk a little bit about philosophy. So there will be various points where I will try to recall the philosophical points that Bruno raised in the previous lecture, and just, give you further motivation for why we should bother to study category theory. And then weaving through all of that, we will try to understand some of the key concepts of category theory. So categories, objects, morphisms, and functors will be our key objects of study today. And we will do this in a sort of mini tutorial form. So it'll be a way for you to get well versed in the basics of manipulating these objects. So it will be a kind of mix of I will be talking to you about certain objects and concepts that you might want to be aware of. And there will be some interesting exercises interspersed with that to give also you the opportunity to contribute in a meaningful way to the discussion. So actually today's lecture will be a bit interactive in that there will be various points where you will be able to directly try to give answers to some questions that I will raise on the spot. I think the Q&A feature is the best way for you to interact with me in this way. So if at any point there is a question that I raise and you would like to offer an answer, please write that in the Q&A section. Or if at any point in this lecture I say something that you find confusing, please also use the Q&A feature, and I will try to respond to it whenever it's most convenient. And because really what we're teaching about, what we're talking about here is going to be foundational for everything that comes next. And actually, I'm going to need to apologize to any category theorists who are following us today, in that some parts of today's lecture will be, from a category theory perspective, somewhat slow. So basically, essentially, it'll be somewhat slow because we will have to go through these concepts in a kind of step-by-step manner. And it is there for a purpose. We're a very diverse group of people, and not everybody has the same foundations in math for this particular course. But I do promise you, if you come here from a category theory perspective, you will walk away from today's lecture with also some context in how we can use these ideas and ground them in an actual deep learning application. So we will talk about how to formalize the message passing primitive, which is a central component in graph neural networks, to use these kinds of concepts. And then we will explain our recent paper that was accepted for NeurIPS 2022 using the concepts that we will discuss today. So there should be something for everyone in this particular setting. I saw that there was a question on why not use the Zoom chat instead of the Q&A. I see Pim is probably going to write an answer to that, but basically I think the chat is disabled because we had some instances of improper use last week. But yeah, the Q&A will be more favorable in this regard. So there is a piece of work that started all of this discussion in category theory, and it's this foundational paper from Eilenberg and McLean from 1945, which actually, in that very paper, the authors themselves highlight how, as we now say, category theory could be an extension of geometric deep learning. They actually write very explicitly, category theory can be seen as a continuation of Felix Stein's Erlangen program, which, for those of you who have a background in either group theory or in geometric deep learning, you will find this very familiar because it's the foundation of how we build architectures in geometric deep learning. But there is this paper that kind of started it all, but the focus was always a little bit on mathematicians, so to speak. Like most of the top category theory texts, at least the earlier ones, are geared towards abstract mathematical applications, and therefore they are not necessarily super accessible to someone who might be coming at this from, say, a machine learning perspective. And one of the things we're going to be trying to do today is dive into the realm categorical while trying to tame all of these dragons that you might encounter if you were to go out on your own and try to dive through all of these papers. Bruno actually already shared on the Zulip many interesting resources that you might want to read through if you are a machine learning person looking for machine learning person accessible category theory tutorials. But we hope that the one today will also be quite complementary and maybe a bit more zoned in to what deep learners might find particularly useful. So that was a fairly long-winded introduction, but I thought it was important to kind of get the ball rolling and make it very clear what our context for today is and what we're going to try to achieve, so that hopefully everybody has the right takeaways from today. And basically, we are now going to first start by answering the very simple question. We're dealing with categories and category theory. Can we now make it very concrete? What is a category? This is something that Bruno hinted at during his lecture last week, but now we're going to try to give something that's more formal as a definition for what a category is. It's actually a remarkably simple concept when you start with it, right? It gets complicated the more you work with it, but in essence, category theory deals with a fairly simple set of constraints. So what is a category? A category is a concept that consists of two things. The first one are objects, and we say those objects form some kind of universe. I will explain briefly in a few slides' time why I use the word universe rather than set of objects. TLDR, it's to avoid various kinds of paradoxes emerging, but basically you can think of it as some kind of collection of objects. And then you can have morphisms or arrows between those objects, okay? And that's the main setup of what we're interested in category theory. Now, of course, like this, the way it's phrased right now, especially for the graphy people in the audience, you might say, yeah, this is just directed graphs, right? But there are a few constraints that need to be respected here. And specifically, for every object in a category, there must exist a unique identity morphism that maps that object to itself. And if you have a morphism from A to B and a morphism from B to C, you must be able to compose them using this circle operator. So you have this G circle F, which maps you from A directly to C by composing the effects of F and G together. And also composing a particular morphism with an identity morphism in the right place will give you back that same morphism. And also associativity must hold with composition. So if you have any three morphisms that can compose with each other, so F from A to B, G from B to C, and H from C to D, it shouldn't matter in what order you choose to compose them in terms of bracketization. You will get exactly the same morphism as a result. And another concept which is often useful to think about is you can also talk about the collection of all the morphisms from A to B. It's often denoted with this HOM of A-B notation, sometimes also referred to as the HOM set. So when I say HOM A to B, it is the collection of all the arrows that start in A and end in B. And obviously, this is a fairly bland set of rules to look at like this, and it's not very easy to visualize them when you think about them in this way. So actually, what we very often do across both applied and pure category theory is to visualize these kinds of objects and morphisms through the use of these commutative diagrams. So you can imagine basically a sort of directed graph where you take the different nodes to be the objects and the arrows mapping one to the other to be directed edges in this graph. And why do we call them commutative diagrams? Well, what the meaning here is if you look at any pair of paths to get from one object to another, it should be exactly the same morphism. So, for example, if I want to, in this particular commutative diagram, if I want to go from A to C, I can either go down the path of first applying F, then applying G, then applying identity C, or I can go down the path of applying G circle F, or I can go down the path of applying identity A, F, G. All of those are different paths, so different ways to get from A to C, but they all, because of the rules of category theory, must compose to form exactly the same morphism. So that is basically the nutshell of category theory, the main ideas, and everything that we make will have to conform to these basic rules. And it's a very simple kind of compositional structure that, as Bruno was discussing, we would hope to encode in the objects that we are studying. And one thing that's very critical, and it takes a while to appreciate it, and we'll see very concrete examples to help us appreciate it, is that we do not assume any knowledge about what's inside the objects, okay? So for us, objects are just, abstractified atoms like A, B, C, or whatever. We don't really have the permission to peek inside those objects and see what's inside them. And this is actually great for us because it will allow us to focus on the structure of the computation between those objects. So those will be the arrows between them, and not get bogged down in the specific details on what that data is and how it's being operated on. This is an idea that Bruno already conveyed in various ways in the previous lecture. I'm just restating it here to make it very clear. And as already mentioned, when you have this kind of setting where objects are completely abstractified and you're just focusing on the structure between them, it's an excellent recipe for discovering connections, not only between different areas of math, but as we will see throughout this course, between various areas of, say, computer science and deep learning, and various forms of mechanisms in neural networks like backpropagation and stuff like that. And once again, I will actually quote back the excellent slide that Bruno had in his previous lecture. So with category theory, we have this kind of bird's eye view of mathematics where all these objects have been abstractified and they're just, identifiers and nothing else. And from this high in the sky standpoint, the details become invisible, but you can spot patterns that were impossible to detect from the ground level. So there is a question being asked from Kartikeyan of, if we're not allowed to peek into the objects, how do we define useful morphisms? Basically, the structure of the morphisms will be given by the category that we decide to use, and we'll talk about this in detail when we dive into examples in the set category. For now, I will just say, basically, this is something that should hopefully become obvious when we start to play with these things. But basically, the morphism structure is something that we assume given to us. And we can use what's inside the objects to define the morphisms, but when we do the analysis, we are not allowed to peek into the objects. I guess that's a more qualifying way of saying that. Okay, now one thing that's very important to note is I've given you examples of categories, and I've drew this one diagram with nodes A, B, and C. And effectively, what I haven't told you, which should be obvious from the definitions, but I still think it's very important to spell it out, is what is an example of a non-category. So one thing we said, categories must have identity morphisms. So if I, for example, get rid of the identity morphism for node A, this is now no longer a category. It doesn't conform to the rules. Similarly, every possible pair of morphisms that can compose with each other must compose with each other. So a composition must exist. So if I choose to remove the G circle F from the diagram and assume it doesn't exist, then also this would not be a category. It doesn't satisfy the compositionality requirements. And why is this important? It's because, there's a lot of arrows that one needs to draw if you want to specify every possible morphism between objects. These are just the simplest possible examples. But we're not, to show some interesting pieces of structure and interesting pieces of computation, we're not going to draw every single morphism that's in there. For example, we will often ignore the identity morphisms just to keep the picture looking cleaner, right? But why I'm showing you this is so that you know that if I ever show you a categorical diagram which doesn't have identities, that doesn't mean that the identities are not there. Or if I show you two morphisms that should compose, but I don't draw their composition, that doesn't mean the composition is not there. It just means I've chosen not to draw it in order to help you focus on what's important. But know that if there's an object, there must exist an identity morphism. If there are two morphisms that can compose, their composition must exist as well. So just keep it in mind that we're always able to draw them. We can just sometimes decide not to. Okay. There is a question here on, does G circle F need to be unique? And yes, it does need to be unique. So for a given F and G, such that the endpoint of F matches the start point of G, then basically G circle F needs to exist and it needs to be uniquely defined. And then if G and F are invertible, is it a category? That's a very good question. We need to be very careful on defining what invertibility actually means. And we will get to that. Like, we cannot very easily throw around the word invertibility in category theory, but we will get to that, I promise you. And then there's the question of, does category theory also deal with non-categories, or is the concept general enough to be exhaustive? Well, that's an interesting question that I think I will actually let the category theory experts comment on that one. But I would say that it is possible to construct a meaningful category which follows all the rules to encompass basically any situation that you actually care about. So it's, yeah, it is possible. Sometimes it might require a bit of work. Okay, so hopefully this answers the most burning questions of what the basics of categories are. But giving you a bunch of abstractified concepts and not going any further with it is not a good recipe for understanding. And I'm a firm believer in learning by doing. So before you go read a book on some deep learning concept, just go out there in the wild, try to write some code, see what happens, and learn by trying. And that's exactly what we're going to do here. So I've given you the basic playing rules of this game. Now we're going to dive into a concrete category and try to play around with it as much as we can within the time that we have. And then we'll obviously dedicate some time at the end for some more interesting concepts. And specifically, the first category that at least people who come from a computer science background will want to focus on at the start is the category of sets, or the set category. And as we said before, how do we define a category? You need to define the objects and you need to define the morphisms. So whenever I try to introduce a new category, or whenever you want to use a new category in your work, the first thing you need to do is say, what are the objects? What are the morphisms? And the typical standard example that we're going to focus on right now is the set category, where our objects are sets and the morphisms are functions between them. So you can imagine a situation like this here. As I told you, we're not allowed to peek into the objects, but now I've just for a second assumed that you can. So an object might be a set, like this set A on this slide, and you might have another set B also drawn on this slide. And you can then have a function f between them, which takes every element of A and maps it onto some element of B. And this is one particular slice into what you might see in the set category. And one thing that's important to note here is this is the reason why I said the objects form a universe rather than a set, because in this particular case, you would need to define a set of set, and this can lead you into very tricky situations, such as Russell's paradox, where if you're allowed to say define the set of all sets, then you run into these interesting questions. For anyone who's played Portal, you've probably come across this as well. Does a set of all sets contain itself? So the notion of a universe, which I'm not going to dive into too much, is just a way to define a collection in a way that these paradoxes do not happen. Okay, but as we said, well, first, I think it's a very good exercise for you to try to do after this lecture, to take this idea of I have a category where objects are sets and morphisms are functions, and just informally or as formally as you like, convince yourself that this construct satisfies all the axioms that I showed you a few slides ago. But critically, as I said, we're not allowed to peek into the objects, so our category is oblivious to what's inside the sets. Like, you don't see the elements of A, you don't see the elements of B. All you see is one object A, one object B, and you see an arrow F connecting one to the other. And you know, as anyone who's done any bit of machine learning, you might wonder, does this drop a lot of data? Like, fundamentally, it feels like it should drop a lot of data. However, I would actually argue that this doesn't really drop a lot of data at all. And I will try to actually show you a result that, at least to me, was mind-blowing when I first come across it. With hindsight, it's probably not that complicated. But when I first come across it, it really blew my mind, and it really got me to think more about these kinds of categorical things. So specifically, let's try to use the structure of the set category to identify certain kinds of special sets. One particular special set is the set that has exactly one element. For those of you who have done any functional programming before, effectively, you might remember unit as the data type that gets returned when your function just does a side effect or something like that. And okay, so now let's see how we can talk about morphisms from any particular set A to the set that has one element. So can you please, can anyone use the Q&A function and tell me what are the morphisms from a set A to the set that has exactly one element in this category? Yes, exactly as Frank says, there is exactly one morphism that maps a set A to the unit set. And that's exactly the function that returns always that one element for every single element of A. And actually, this property only works for a single element set. It basically uniquely defines it up to isomorphism. And one point about this up to isomorphism remark is that in category theory, we will very rarely talk about things being purely equal or purely unique. And that's because we do still drop some details about the objects, but we often talk about this as being like equality for all intents and purposes. So I can identify one single element set by just a set that has this property that no matter what other set I choose, there will be exactly one morphism into it, and that is the constant morphism. So you might end up basically with a diagram that looks like this. So you have, you know, the collection of all possible sets, and you're hunting for this gadget where every single set maps onto the unit with exactly one arrow. And this is a pattern that you can try to find in the arrows. And it uniquely identifies the unit element. In a categorical perspective, unit is what is commonly known as a terminal object. So whenever you have a category and you have this kind of pattern where every object maps to this particular object with exactly one morphism, that object is known as a terminal object. And once again, I never needed to look inside this set in order to define the unit set. I just had to look at the arrows. And there's already one instance of what we can do without dropping a ton of data and doing something interesting. But okay, so now by finding this gadget, we have been able to identify the unit set. And now you might wonder, can we then use that to say something about other sets? So let's say I have the unit set here, and I have some other set B on the other side. And here, just for convenience, I've numbered the elements of B 1 to 6, but that's beside the point. Can you tell me something about the morphisms from the unit set to any other set B? What are the morphisms from unit to B? Yes, exactly. As Vitaly pointed out in the Q&A, there is one morphism per element of B. Each morphism isolates one particular element of B. So it maps this unit element to every single element of B. And in fact, for those of you who have done functional programming before, you might recognize this as a constant function, and that's the way in which in functional programming we define constants as functions from the unit set to the particular set of values that our problem is concerned with. And for all intents and purposes, you can identify these 6 morphisms with the 6 elements of the set B. So now our diagram gets extended in this particular way where we've identified the unit, and now we look from the unit to a particular element B, and we see that every single morphism uniquely identifies an element of set B. So what have we just done? We have, as Shivam notes, we have basically reconstructed what's inside B without ever peeking inside B. That is the mind-blowing result that I found for the first time. So even though you have completely ignored the structure of what's inside these sets, you have been able, through a sequence of detecting patterns in the arrows, you have been able to reconstruct everything, well, up to isomorphism, everything that's inside these particular sets just by looking at the arrows. And that is, in my opinion, what makes category theory so powerful. It abstracts away so much of the information, yet it's still expressive enough for you to be able to recover, for all intents and purposes, everything that's inside any particular sets, because the morphisms from units to that set are not really distinguishable from the elements of that set in principle. So in summary, maybe just to kind of hammer that point home, category theory allows us to detect these patterns in computations because we take the bird's eye view of the morphisms without focusing on the specifics of the data that those morphisms operate over. And basically, all of this is done without drastically losing information. And as a result, category theory is going to be perfect for our purposes of trying to explain away different facets of deep learning through the lens of compositionality. And generally, it's proven to be a wonderful tool to connect disparate areas of math together. Okay, so that was just one single teaser result to hopefully get you interested in the kinds of mental math we're going to be working on today. But that's just one out of many examples that I've prepared for you today. So let's dive into it. Let's try to define some other interesting categorical constructs over the set category where things will still feel familiar because the morphisms will exactly correspond to functions and it's going to be a bit more natural to think about them. Okay, so what we're going to do. What we've talked about so far, like we've defined a category, we've used some concepts of categories to define a terminal object, and then we've shown that once you find that terminal object, which in the case of a set category is a single element set, you can use that to actually reconstruct everything about your sets. So on the surface, it gives you a very simple set of rules to follow, but you can then build on top of those rules to define a lot of other exciting things. So basically speaking, we will take these rules and now derive some other interesting constructs that build on top of them. Here is just a bucket list of the things we're going to cover during the lecture today. But as you will see, the deeper down the rabbit hole we go, these things can quickly get more complicated. So like just because things appear simple in the context of this lecture, things can get out of hand very quickly. So we have to be careful, we have to tread carefully, and we have to kind of build our muscle memory before we dive into any generic category theory text, basically. And that's basically my hope for this lecture. If you haven't seen these kinds of concepts before, I'd like to get you comfortable enough with them to be able to discuss them. So one thing, let's just start from what we just defined. So we have been able to define effectively in the context of a set category, a single element set, which we call the unit set. Okay, and we said that that is the terminal object inside set. It has this property that, in general, for any category C, we can say an object T is terminal inside it. If for all the other objects A, there is exactly one morphism that maps A to T. So the cardinality of the Hom set from A to T is equal to 1. Now, naturally, you should be able to take this idea, which gives you a terminal object, and just flip the definition on its head. And that should also give you something special, right? And basically, it leads you to a dual definition of an initial object. And specifically, we can say that object I is an initial object in a category C if for all the other objects inside the category, there exists exactly one morphism that maps I to A. So the Hom set of I to A is equal to 1. And now we might wonder, what is the initial object inside the set category? And let's try to think about this, right? So in the set category, the morphisms are functions, right? So we want to have some construct where the number of functions will be exactly 1, but it's good for us to reason about the number of functions. So if you want to talk about how many functions there are from a set A to set B, you probably know this from combinatorics. The number of such functions is B to the power of A. And that's why, as we will discuss later today, functions are also sometimes called exponentials. Now, obviously, how did we look at the terminal objects? We found that a single element set unit has cardinality equal to 1. And as a result, 1 raised to any power gives you 1, and therefore the unit set is terminal. Like the Hom set will always be of size 1. So how can we then use this idea to define, sorry about this, to define a initial object? So something where the A is fixed and B can vary and the number of functions is equal to 1. Well, you know, the only way in which you can recover 1 by fixing the exponent is if you set it to 0, right? And this is basically saying that our initial object A should be the empty set, okay? But this actually raises a bit of a existential question, right? What is even a function from an empty set to some other set, okay? Now, just by the very definition of what a function is, a collection of ordered pairs from one set to the other which satisfy certain properties, you know, by definition, a function from an empty set to some other set must exist. You just take the empty set of ordered pairs, and that's your function from empty set to some other set. However, because this function never can really take any values, you're never really able to call it, right? So, well, it turns out that functions like this are already thought about in languages like Haskell, like functional programming languages. They're often called absurd, right? They're absurd because you're unable to call them. And they map from the void type, which is the empty set, to any other type. And there's exactly one such function for every single set. And you can think of it as the logical equivalent, functional programming equivalent of the logical statement, from false, I can prove anything, right? So give me an object of the empty set and I will give you anything you want, right? You're never going to be able to give me an object from the empty set, so I can never do this, right? So in this particular case, our initial object actually is the empty set, and there does exist that one function from the empty set to every other set. That is, in Haskell terms, the absurd function. And there's another very interesting, aspect that you might want to add on top of this. Is that we talked about this initial object and terminal object, and they were in many ways duals of each other, right? We took the definition of the terminal object, we flipped the two definitions together, and we basically recovered one from the other. And specifically, what does this mean from a categorical perspective is that if I were to take the morphisms in one category and then reverse them, so make the endpoint become the start point and vice versa, I would end up basically rederiving the concept that I care about. So initial objects, if I reverse my arrows, become terminal objects, and terminal objects, if I reverse my arrows, become initial objects. And this idea of reversing morphisms all at once turns out to be a super powerful way in which we will basically be able to get duality, so dual concepts at the same time, pretty much for free. So this is the idea of the opposite category, or C op for a particular category C. And it's defined as follows. So as we said before, to define a category, you need to define its objects and its morphisms. So the opposite category, C op, has exactly the same objects as C. And for every morphism F that maps A to B inside C, there must exist that same F that maps B to A in the opposite category. So I've literally just taken all the arrows in C and I've flipped their direction. I need to also do the same thing to compositions, right? So whenever I compose G and F to get from A to C inside the original category, I must then compose them the other way around to go from C to A in the opposite category. And this definition can also be applied vice versa, going from C up back to C. So in a way, the opposite of the opposite category is the category itself. And this is a very nifty concept that allows you to basically for free get a bunch of things as just duals of things you've already defined. And let's try to take some of these concepts and take them a step further. Let's try to generalize some more things that we can find inside sets. So we can actually recover many interesting categorical constructs just by taking things that we know from sets and then generalizing them directly. For example, morphisms seem to appear quite similar to functions in some regards. Just to answer Piotr's question, the morphisms in the opposite categories do not have to be inverses of the original morphisms. So the axioms do not assume that. Exactly, that is true. And so what's the meaning of the opposite category of sets? So basically, if I have a morphism A to B in set, and that's a function from A to B, a morphism from B to A in the set up basically says, there's an arrow from B to A if I have a function from A to B, which is defined in this particular way. So it's really just defined by taking the concept in the original category and kind of flipping it on its head, really. Basically now, so you get something that looks like a function, but you have to, like your codomain becomes your domain in a way. Okay, so one thing that you might want to exploit is that functions have certain properties that make them special. And let's see, can we take some of those properties and generalize them to the general categorical setting? One such concept is that of the surjection. So we can say that a function is a surjective function if every element of the output set B is mapped to by some element in the input set. So it completely covers the output set. Can we now define something like this for generic morphisms that map from A to B? Once again, you cannot take this definition that I gave you above, where it's a surjective if it's every element of B is f of A. You cannot do that because you're not allowed to peek into the objects, right? So in order to define what a generalization of surjective functions is for morphisms, you can only look at how those morphisms compose with other morphisms. You're only allowed to look at the arrows. And let's try to make this concrete. So let's assume we have another set. So we already have elements A and B inside set. And now we have another element C. So, and we have a function F, which is a morphism from A to B in the set category. What happens when you take a surjective function and then you compose it with any other function G? Like, what is special about this composition? Can we get any thoughts in the Q&A? So the first suggestion, okay, the composition is a function. Yes, you will have defined something from A to C, but it will be done in a very special way, right? Essentially, because your F fully maps to the space of B, then you will be able to use the full power of G effectively. So F applies and it's surjective, it will cover all the elements of B. So then G maps B to C and every single aspect of G will be used. And what this means is I cannot offer you a different function h such that composing h with f will be the same as g composed with f. They have to be exactly the same because of the surjectivity property. And this then leads us to define a concept of an epimorphism, or sometimes known as an epic morphism. So this generalizes surjective functions to arbitrary morphisms in any category. So we have a morphism f, which maps object A to object B in some category C, and it is an epimorphism if for any two morphisms G and H that I take that map B to C, if those two composed with f give you the same morphism, then they must be the same. This epimorphism property of f forces this restriction. And now, of course, in the set category, you can show that functions that satisfy these properties are exactly the surjective functions and nothing else, right? And as we discussed before, you can flip this concept on its head, like by reversing the arrows in the opposite category, and generalize the corresponding concept of injective functions, obtaining the concept of what's known as a monomorphism. So a morphism f, which maps A to B, is a monomorphism if, once again, I can give you any pair of morphisms G and H, but this time they map C to A, so it's a pre-composition rather than a post-composition, such that if the composition of G and H with F gives you the same results, then H and G must be the same. There doesn't exist any other situation in which this can happen. And, you know, as you might expect, because these are really concepts obtained by reversing the arrows, a monomorphism in C is an epimorphism in the C op, the opposite category, and vice versa. So any epimorphism in C op is a monomorphism in C. And another concept that's quite important, and you might think about now, because we talked about injections and surjections, in the land of functions and sets, when you combine these two properties, you end up with bijections, so functions that you can invert. And this now finally lets us define what an isomorphism is. I've seen several questions asking what an isomorphism is, and now we can finally define what it means categorically. So specifically, we need to be able to talk about some kind of inversion, but we cannot really say inverses, because typically when you have a function f and an inverse f to the -1, it doesn't matter in what order you compose them, you get identity both ways. But now the exact outcome of composing an f with this quote unquote inverse is different depending on what order you choose to compose them in. So we say that some morphism f that maps A to B is an isomorphism if there exists this complementary morphism G that maps B back to A, such that composing them together, you get identity. But this is the catch. If you compose F with G or G with F, you will get different identities because you will land in different objects, okay? And one other thing is that you can see directly that this definition, if F is an isomorphism, then G is also an isomorphism. But be careful with using the term inverse for G, because generally speaking, it's a bit unexpected that when you compose F and G and then G with F, you get different results, okay? And whenever you say that two objects are same up to isomorphism, then you imply that if I demonstrate, you say two single element sets in the set category, there must exist some isomorphism mapping between them. So in some sense, from a structural perspective, they are exactly the same object. Now, you might be very tempted to say, because, you know, I've generalized surjections to make epimorphisms, I've generalized injections to make monomorphisms. And, you know, in set land, we say that bijections are injections and surjections at the same time. So you might be tempted to say that a morphism is an isomorphism if and only if it's both a monomorphism and an epimorphism. Like this would be kind of a direct application of a rule, you know, from sets land with functions to a more generic case. But is it actually the case? Well, here is a very simple category with only two objects and exactly one morphism that's not an identity. And it's a nice exercise. I invite you to convince yourselves that in this category, F is both a monomorphism and an epimorphism. So it satisfies both of those rules that we would expect from generalizing injectivity and surjectivity. However, it's both of these things, but it's not an isomorphism because there is no way to get back to A, right? You apply F and there exists no morphism G that would take you back from B to A. So here is one very simple example that shows you need to be careful when taking a concept from sets and generalizing it to categories. Things that work or feel natural in sets may not be true at all when you generalize to categories. So here is one simple example. However, the converse is true. So if you have an isomorphism, it must be both a monomorphism and an epimorphism. It's just the other way does not work. Okay, so we studied interesting concepts around morphisms just now. So we tried to generalize ideas from functions, specifically injections, surjections, and bijections, and tried to come up with morphism constraints that leads morphisms to behave in a similar way. And we can, as you might expect, also define similar kinds of constructs over objects. So what are some interesting things we might want to do over set structured objects? One common thing is we might want to pair them up, so to reason about pairs of objects. This is often very important in functional programming when we have to carry all of our arguments together with us. So this pairing up with elements of two sets is in setland known as the Cartesian product, A times B. And the elements of that Cartesian product are just ordered pairs A, B, where A comes from the set A and B comes from the set B. Now, for certain categories, and definitely including the set category, the concept of a product can be generalized. So the situation we have is we have two objects in a category. So A and B are objects in category C. And we want to define a product object A times B, which is also itself a member of C. Now, this will not be possible to define for all possible categories. And in future lectures, we will talk about what are some of the conditions that a category must satisfy for these things to exist. However, for now, we just assume that the category satisfies those properties. Now, what do we need to provide to say that this object is a viable product object? So effectively, we need to have some way of attaching some morphisms with which A times B can interact with both A and B in a meaningful way, right? So specifically, one very natural thing that we need to be able to do is to equip our product object with these two so-called projection morphisms that will tell us for a pair object which part of that pair object came from A and which part of that pair object came from B. So we have these two morphisms, PA and PB, that take our proposed pair object and give us something that's belonging to A and something that's belonging to B. So the diagram of what I just explained to you is illustrated in the bottom right of this particular slide. So basically, you have here this particular construct. Now, what is a problem with this, right? I mean, this particular situation where you have, say, three objects and two arrows connecting things in this way, this is something that you get all over the place. Like in the set category, you pick any three sets, I can very easily illustrate to you the two arrows that are necessary in almost all cases, right? So now the question is, what is it that makes A times B special in this regard? So basically, there could be many objects X that could also claim to have these projection morphisms FA and FB, right? So what is it that makes A times B the special object? There needs to be something really special about it. Specifically, what do we think of as the product object is it basically has a minimal combination of data in A and B, right? So it's literally no more and no less by just taking something from A, taking something from B, and concatenating it, right? So if any other object X claims to present projection functions, it's not just concatenating A and B together, it is actually doing some more stuff on top of that, right? And basically, what this means is that I can undo that stuff and go back to the original pair of objects that produced this particular candidate X, right? So what this really means is that if A times B is the true minimal explanation of a pair of objects, effectively, it must be that I can take these two, imposter projections, FA and FB, and they must be decomposable in a way that I first undo this extra processing by running F, this morphism F, and then running the true projections PA and PB, right? So basically, it must hold that these candidate projections FA and FB actually would decompose into F composed with PA and F composed with PB. So A times B is actually defined as this product object that is a unique object up to isomorphism always, such that for any other object X that claims to be the product, you must be able to decompose its morphisms using the true projection morphisms. So yes, so there was a question on if I understand correctly, A times B is only defined up to isomorphism. Yes, that is true. So there could be many equivalent ways to specify A times B, and those are all isomorphic to each other in this particular case. So one thing that's important here to note is that what we're really doing here is we're taking, the collection of objects and morphisms inside our category, and we're hunting for patterns, right? How did we find the unit set? We hunted for a pattern of every other set points to this guy with exactly one morphism. Here, we're hunting for the product object by finding this object that has this kind of pattern around it. And basically what we're doing here is we define an object that has a certain property, and we look for a specific diagram of morphisms around it that uniquely defines it. And this particular diagram uniquely defines A times B up to isomorphism. And as you might expect, everything that we have in the original category also has a dual concept in the opposite category. So if I were to, just maybe to go one slide back, this was the diagram that brought us to the product type, the product object. We can now flip all the arrows and end up with another diagram that we can hunt for, where now the projections are pointing the other way around. And this leads us to the so-called coproduct in the opposite category. And now one interesting question here, and I will leave it as an exercise because I think it's a very interesting thing to ponder, is what would the coproduct be in the set category? If you have some idea, you can write it down in the Q&A. I will basically kind of keep going, but it's a good thing for people to ponder what this coproduct A coprod B actually is. It is a very established set mechanism for combining two sets. It's obviously not a Cartesian product, it's something different. Okay, and I want to go through one more example of an interesting object structure or pattern that we can hunt in these categories before I try to define some more advanced concepts. So one more piece of exercising some muscles in category theory. The last construct I want to generalize is the notion of functions. So because the way functions are defined, you can define them as the set of pairs in the Cartesian product satisfying certain properties. Specifically, it's the set of all pairs from A to B such that there is exactly one pair for every element of A, right? And this means now that the set of all functions from A to B is itself a set. So for any two objects, A and B inside set, I should be able to also define one object in set, which is the set of all functions from A to B. And over general categories, we cannot always define this object, but when it exists, we generally refer to it as the exponential object, or B to the power of A. This is obviously related to that cardinality argument we discussed before, where the number of functions from A to B is equal to B raised to the power of A, right? And as before, so when we define the product object, we needed to equip it with some morphisms to project A and B from it. right? So now similarly, we need to take our functional object, b to the a, and equip it with some morphisms in order to complete this definition. So we're going to use similar kinds of ideas. It's just going to be a little bit more tricky, right? So what is it really that something needs to be functional, right? So this b of a, its elements are functions. And in general, the exponential object over an arbitrary category, if it exists, will generalize the notion of sets of functions. So what can you do with a function? You can evaluate it, right? So there must be some morphism which is kind of related to evaluating the function. So this morphism v takes our exponential object and then takes a input to this exponential object, or in the case of sets, inputs to the function, and basically gives you the output, right? So you can read this signature of morphism v as, if I have a function and its input, I can evaluate the function on that input to obtain the output. Now, of course, note that here, in order to give this morphism to you, I needed to define a product of the exponential with a. So I'm also assuming not only that exponentials exist, but also that products with a can be defined. So all of these things are subtly assumed, but we're assuming that they're possible. And as I said, in future lectures, we will talk when is it okay to define these kinds of things. And now, of course, just like we had it with coproducts and products, we could actually have many possible objects X that claim to have this evaluation morphism. So there can be an object X which claims to be b to the power of a, and it might present itself with a morphism E that takes X and takes the input A and gives you B. So how can we tell which object is actually the exponential object? Well, just like so, this is just kind of a direct application of what we did with the product type, really, right? So if this X is not truly an exponential type, then it's capturing what the function is doing, but then it's also capturing some other stuff on top of that. So there must exist this kind of unique morphism U that can map the contents of X to the actual exponential object. And in such a way that then this reduces to constructing the product of b to the a and applying the true evaluation morphism v. So you get a diagram that's a little bit like this. Now, of course, it's a little bit more complicated than what we looked at for product types. So maybe it is better to write it in a bit more elegant form, maybe with a bit of abuse of notation. It looks something like this. So basically, if I have an exponential object pretender X, and I have my evaluation morphism pretender E, which takes X and input to produce output, we can show that b to the power of a is actually the true exponential by demonstrating that X times a maps to b to the a times a using this intermediate morphism U, and then running the true evaluation morphism V to evaluate the function. And just like before, in this case, you can use the opposite category to take the notion of an exponential object and define a co-exponential object. And I think it could be an interesting exercise to ponder, especially if you haven't come across these terms before, as what would this co-exponential actually mean in the case of the set category. I think it's not necessarily a very simple thing to ponder, but it's a good thing to kind of think about to see how well you understood some of these concepts and relating them back to what's happening inside sets. And I'd be very happy to keep the discussion going on that on Zulip after the lecture is over. And maybe one more fun part for the functional programmers in the audience for this particular function application is that in the set category, at least, we can use this idea of exponential objects to explain also partially applying a function. So if you have a morphism, a function f that maps a pair of objects, x times y, to some output z. So this is, you can think of this as a function of two arguments. You can actually reinterpret that as a different morphism, fc, that, and I'll explain why I'm using the character c in a second, that maps x to the exponential z to y. So what does this mean? Like if I'm going to read it out in like layman's language, it means I have a function that takes x and y and gives me a z. This means give me an x, and then I'll give you a function that maps y to z, right? Which is a function that partially applies the x argument and then is waiting for the second argument. Are there any functional programmers in the audience? Can you tell me what have I just defined? This should be a very famous concept in functional programming. Yes, exactly. I see a bunch of people saying it all at once. I have just given you currying. So to functional programmers, currying should be a very familiar concept. Here it is in Haskell. You can take a function that takes a pair of objects and gives you an output and curry it out to give you a function that takes the first object and then gives you a function from the second object to the result. And one thing that's really cool is that this concept of currying can be generalized beyond the set category to any category which is closed monoidal. In the future lectures, we will talk about what monoidal categories are. So this is not something for us to discuss right now, but hopefully this is, just another example of how you can take something that you're familiar with in the context of functional programming and kind of generalize it using the language of categories. Okay. I would also, before I start to define functors, I would also like to acknowledge that, we talked about all of these things in the context of sets, but I would also like to say that obviously set is not the only category in this world, and there are other categories that you might want to think about. And therefore, I'm just going to show a few examples that take this idea and map it beyond the set category. So one thing that in this context I really want to say is that any result we get from category theory are obtained under the assumption of what is the category we work in, okay? And therefore, it's very often an important first step in any category theoretic derivation to establish that, to establish what category you're working in. And to give you an illustration of that, let's consider the category of relations. So this is the rel category, where our objects are still sets, so just like in set, but morphisms are no longer functions. Morphisms can now be relations. So a relation is a more generic concept that generalizes functions further, and functions are relations, but not all relations are functions. So can someone tell me what would the initial and terminal objects be inside the relation category? Does anyone have any idea? What are the sets from which you have only one relation going into it or only one relation going out of it? Yes, it is actually the empty set, as Frank says, for both initial and terminal objects, okay? So actually in rel, both the initial and the terminal object are the empty set. And this is already one result that is different for the rel category compared to the set category, where in the set category, only the initial object was the empty set, but the terminal object was the unit set, okay? So that's this is just a very clear example of how if you have a concept that works over the set category, that concept need not necessarily be the same when you go to even a slightly different category like rel. One fun exercise that I'd be keen to see your thoughts on after this lecture is if we take products and coproducts, they also exist in the category of relations. What would they be? We said that products in the category of sets are these Cartesian products. We left coproducts as an exercise. What would they be in the category of relations? Okay. So that was still something that was very set adjacent. Now, so to answer Dobrik's question quickly, the empty set is terminal inside rel because there exists exactly one relation from any set to the empty set, and that is the empty relation. And you can see the definitions of what's a relation to verify that this is true. Okay, so now I'm going to talk about something that's maybe a bit less aligned with discrete math and a bit more to say something that might be interesting to group theory or geometric deep learning, and that is the concept of a group. So a group, as you might know, is a set G which consists of a bunch of elements, which we often think of as transformations. And we have this composition operator, GH, that lets us compose two different group elements together in such a way that a bunch of axioms are satisfied. So we want this composition to be associative. There must be a unique identity element in the group that satisfies the usual requirements. There must exist inverses to every single group element, and we must have closure. So for any two group elements, the composition of those two elements is itself in the group. These objects turn out to be critical for the study of geometric deep learning. Pim will tell you all about them in lecture 4. Here, I just want to give a bit of a bird's eye view into these groups. Here on the right-hand side, you can see actually my favorite symmetry group, which is the group of all rotational symmetries of the Rubik's Cube. So how can we talk about groups inside the realm of categories? Okay, now, there are some ways in which we can approach this, but because we talk about these group elements usually as sort of transformations. So here, the group elements are the rotations of the cube, right? So they're kind of like acting on data. So we can think of them as morphisms in a categorical sense. And what do we need those morphisms to satisfy that a category doesn't already give us? Well, first, we need the identity to be unique. So there needs to be exactly one identity. So all of these identity morphisms need to be the same. And remember, in a category, we don't get exactly one identity morphism. We get one identity morphism per object, okay? Then we need to make all pairs of morphisms composable so that closure is satisfied. And in the domain of group theory, all pairs of morphisms can compose in a group, but inside categories, you can only compose morphisms if the endpoint of the first morphism lines up with the start of the second morphism, okay? And lastly, you need to make all of your morphisms invertible to satisfy this g to the -1 existing. And remember, you only get an inverse or something like an inverse if your morphisms are isomorphisms. So let's just look at the first two conditions for now, right? So you need to construct a category such that there will be exactly one identity morphism and such that all pairs of morphisms will compose with each other. Like this immediately defines what the objects of your category should be. Can someone tell me, what does this category look like? What are the objects of this category? Exactly. There is only one object inside this category. That's the only way in which you're going to get exactly one identity and all pairs of morphisms composing. So from the first two prescriptions, you actually say, if I want to turn a group into a category, it must be a category with only one object, which we can call G. And now this gives us that there is exactly one identity, IDG, which is the identity for the whole group, and any two morphisms, because they start and end in the same object, they must be trivially composable. All right. There is a question from Kaio on possible applications of groupoids into geometric deep learning, and Pim is going to tell you exactly about that in his lecture. In fact, his natural graph networks paper directly extends this concept to a groupoid. So be on the lookout for lecture 4. Okay. Now, the last condition that we needed is for inverses to exist. And basically, what we said is that this means your morphisms must be isomorphisms. So the only thing that we're missing really is that for all of these different morphisms that map G to itself, there must also be another morphism that would give us the isomorphism condition. And actually, in this case, I would be comfortable using f to the -1 notation because they're all mapping to and from the same object. So f circle f -1 is the same as f -1 circle f. Like this gives you basically takes you back to the same object that you started from. So I can actually think about it as an inverse for all intents and purposes. Okay. So this is just a quick excursion to rederive groups as categories. And for those of you who have already seen geometric deep learning and saw how many powerful things we can define just by using the concept of groups, now you can see that in the realm of categories, groups are just single object categories. So they're a very small subset of what category theory has to offer. So hopefully this gives another piece of motivation for why using the tools of category theory, we can actually go beyond what geometric deep learning offers us. Now let's define our second key object of the day, which is functors. And actually, everything we've talked about so far was kind of confined to a single category. But the power of category theory truly emerges when you take multiple categories and you let them interact with each other. And just like you were able to define functions between two sets, we can also define functors between two categories. The main difference here is that because categories have objects and morphisms, our functors need to map both objects of one category to another and morphisms of one category to another. Okay. So more generally speaking, if C and D are two categories, then we can define a functor. Here I use capital F to denote that it's a functor rather than a morphism. And it maps objects from C to objects in D and morphisms from C to morphisms in D. It cannot do this arbitrarily, though. This must be done in a way that respects the structure of the input category. And we'll discuss in a second what respecting the structure actually means. So specifically, if there was any interesting structure inside C, that structure should still be present, even if trivially, in the mapping induced by F. Specifically, if I take F and apply it to the identity morphism for object A, I should get back the identity morphism for the corresponding mapped object in the other category. So F of ID is equal to ID of F, so to speak, with the right input arguments, of course. And also, you need to have that compositionality is preserved, trivially or otherwise. You want that if you apply the functor to a composition of two composition of two morphisms, you should get the same outcome as if you first apply the functor to the two morphisms in isolation, and then compose the two resulting morphisms in the other category. So these are two very simple rules, but they're necessary for this functor to meaningfully preserve compositional structure. So let's do it pictorially. So as you know, I like to give diagrammatic explanations of things. So here is one particular category with three objects, as we talked about before, and morphisms F and G and their composition G circle F. So what is now a functor? A functor will take this kind of interesting structure inside one category and map it to similar kinds of structures inside another category. So here I've just shaded the regions for C and D, so I can show you which part here are objects and morphisms of one category, which part are objects and morphisms of another category. And those are the blue and the red regions. And F maps every object in one to objects in the other, and every morphism in one to morphisms of the other. And this is like pictorially what these conditions are really saying. If you have this nice structure in one, you should get that same nice structure when you map back. Now, one thing that's very important to note here, the functor can also collapse things. So it could map A, B, and C actually to the same object in the other category. And we'll see some nice example of this in a few slides' time. But, if you were to split out these objects, even though they're the same, you would still be able to recover this kind of triangular structure, even if it would feel a bit trivial. And John Bayes, who's actually one of the moderators of the Zulip stream that we're using, is actually famously quoted by saying that whenever you have a sufficiently good analogy, it is yearning to become a functor. Like functors are a really good way to describe that there is a pattern in one way of doing math, and I want to see that pattern in another way of doing math. It's a great way to have these kinds of mappings between structure in a way that preserves structure. And to give you one example of a functor, we won't be diving into functors too much today. They'll be far more important in future lectures. But for those of you who are familiar with geometric deep learning or a bit of representation theory, basically I can mention this to you as a possible interesting point just to see. So we talked about how groups can be expressed as single object categories. And for those of you who have done geometric deep learning, and if you haven't, you'll see much more of it in lecture 4 from Pim. But for practical purposes, when we think about group theory in the context of deep learning, we usually mostly care about how these elements of a group act on data, right? So in the context of machine learning, we turn all these abstract group transformations to some matrices such that when we do matrix multiplication with them, they do the transformation that we care about. So this leads us to the definition of what's known as a real representation of a group. And it's just a mapping row that takes our group transformations and gives us these unique matrices such that when we multiply those matrices with our data, it's the same as if we applied the group operation. I'll give a clear example of this in a few slides' time. But what you want to think about these representations as is they give us a way to talk about how our group transforms data in the realm of linear algebra. And actually, we can use functors to make a categorical version of real representations. Specifically, a functor will map these group operations, which we said are morphisms inside our group category G. And we want to map them to morphisms inside some category where those morphisms will be linear transformations, so matrices we can multiply with. And that turns out to be what's known as the vect category, the category of vector spaces. So our functor maps from the single element category G to the category vect. And so vect is a category of vector spaces, as I said, and as we always said, when you have a new category around, you have to talk about what are its objects and what are its morphisms. So the objects in the objects in vect are vector spaces. So they are sets of vectors, and these vectors need to support the usual axioms of addition, scalar multiplication, associativity, distributivity, and so on and so forth. And morphisms, which take you from one vector space to another, are just linear transformations. So they're like matrix multiplications that take you from one vector space to another. And then a functor, which would map this group category to the vector space category, would tell you how to take the group symmetries, so the morphisms inside G, which map that single element G back to itself, to linear transformations for some particular object in the vect category. And as if you remember the definition of functors, and given the fact that G has exactly one object, the element G itself, each particular functor row will tell you how the group acts over one particular vector space. And here is one very concrete example of this for the case of the permutation group. So for any of you who have worked with graph neural networks before, you know that permutation symmetry is a fundamental aspect of how we build a graph neural network. So we want to build operations that are resistant to permuting individual elements in a vector of nodes. And say if we have a collection of 3 elements, we can define the 3-element permutation group as this single object category where the morphisms are just the possible permutations of 3 elements. As you know from combinatorics, there's 3 factorial many of them, which is 6. And we have this identity permutation, which is 1, 2, 3. And now our special representation functor will map our 3-element permutation group into some vector space, for example, the space of 3-dimensional vectors, where each dimension corresponds to an object. And it will map all of our morphisms in the group category to morphisms that map that vector space back to itself in a way that permutes the objects accordingly. So every single one of these permutations defines a unique 3x3 matrix transformation in vect, which performs the corresponding permutation. So you can convince yourself for all of these 6 matrices that when you left multiply them with a vector of 3 objects, the only effect those matrices do is permute the way in which you see those 3 objects. So this is one very clear way in which we can use functors to map transformations of an abstract group to actual matrices that we can multiply our data with and then express various constraints using them. Okay, so what have we covered? We have went through a journey of various categories and categorical contexts, and we have had the opportunity to then use functors to talk about how symmetry transformations act on a particular vector space. And now, finally, for those of you who have been waiting to see a machine learning application, I will explain some parts of our NeurIPS paper using some of these concepts. So basically, we're going to talk about message passing. I hope many of you have seen message passing talked about before in some way, especially in the context of deep learning. And we're going to try to categorify what message passing actually is. So it turns out that even though this is a very simple set of concepts that we talked about so far, we haven't really used the full firepower that category theory has to offer. For example, we haven't yet even mentioned natural transformations, which Pim will tell you all about in lecture 4. It turns out it's already sufficient to explain the key parts of a paper that was recently published in NeurIPS. Actually, will be published in NeurIPS in a couple of months' time. Yes, I will actually very briefly say what message passing is. Thanks for asking, Martha. But this is just to say that it's actually a very critical concept inside the modern deep learning. Obviously, it's not enough. Like, our paper, which uses many advanced category theory concepts to talk about these things, uses many more constructs than what we defined in the lecture today. So there will be some more details that will require more category theory concepts like monoids and monoidal categories, and Andrew will talk about them in a lot more detail in lecture 5. However, let's tell you something about the key idea of what we try to do in this paper, Graph Neural Networks are Dynamic Programmers, which will be presented in New Orleans for NeurIPS in a few months' time. I hope to see actually many of you at NeurIPS at our poster. Maybe we can discuss many of these things in person then as well. So the key thing that we want to try to do in our paper, which is not even in our title, is the fact that we try to formalize what does it mean to send and receive a message in the context of deep learning. And this is a fundamental operation for neural networks to do, because both graph neural networks and transformers, and in some sense, maybe even every machine learning model that you do over discrete data, has to somehow pass messages between instances of that data. And I actually wrote this position paper, Message Passing All the Way Up, where I tried to, in a very opinionated way, say that in a way, message passing is everything. And if you can reason about message passing, then you can explain all of discrete deep learning. But generally, just being able to understand message passing better could lead us to better architectures of deep learning. And how we do that is we're going to try to align the way the messages are computed to the downstream task that we want to solve. And here you have the basic equation of message passing, which I showed in many talks I gave before in the context of GNNs. So imagine you have a bunch of sender nodes that are trying to send messages to a receiver node. What happens is you first apply some function psi, the message function, to compute a vector m, which is sent across that particular edge. And then the receiver node aggregates all the messages that are sent to it to update its representation. So it's a very general and very powerful way to talk about communication between different entities. And the real question we have really is, how do we formalize communication? And to illustrate this, I'm actually going to move away from graphs for a second, and I'm going to talk about a slightly more geometric example. Basically, we want to talk about what does it mean to just generally send messages from one mathematical space to another. Sorry about that. And just to keep things illustrated and kind of geometrically visual, this is an example that came from Andrew, by the way, and I'm very grateful for that. Let's imagine that we want to send a message from data that lives on some set W, for example, a circle and a line. So what this means really is that I have some data that lives on a circle, I have some data that lives on a line. I want to compute data on some potentially different line. So this set Z, okay? And well, one simple way to do this, which is the kind of naive way to do this, is to just kill off the circle, right? And apply some additional function to the line to receive outputs on the line. But that's not particularly exciting, especially because it throws away a bunch of data. So it's not really in the spirit of communication, right? So actually, it might be really good to combine together the data on the circle and the line on some carrier objects that will carry these messages across, and then the line can obtain them at the end. So do you have any suggestions for what could be a good carrier object that would carry data from both the circle and the line? Like, what would be a good object that kind of combines a circle and a line together? Yes, it is a cylinder. Many people have said cylinder. Cross product of circle and line, that is exactly what a cylinder is. So yeah, if you take a product of a circle and a line, you will end up with a cylinder. And that is going to be an ideal space, an ideal set on which we can define our messages. that are being passed. So we can define a set Y, which basically corresponds to this product of the circle and the line, and on it we store messages, and then we can obtain the outputs on our output space Z by just integrating over the circle to get a line again, right? Now, of course, there is the question of we want somehow to go from this state of circle and line to cylinder. How do we do that? Well, we can basically use the data that comes from the circle and the line to as arguments for a function that computes messages on a cylinder. So how can we easily do that? We can lift both the circle and the line into the space of the cylinder by, this is a very common operation in deep learning, by the way. It's a broadcasting operation, right? You're kind of taking a data on a circle and replicating it all across a line. You're taking a data on a line and replicating it all across a circle. And this gives you kind of two cylindrical shaped arguments that you can then directly multiply together to get your messages, right? And actually, this now gives us, it turns out, a very nice way to formalize aspects of communication. And specifically, it gives us this nice diagram of the sets X, which is the arguments for the message function, Y, which is the message space, and in a way that it carries data from a set W to set Z. Now note that there are these three morphisms in blue that in all cases, except for X to W, point in the direction of computation. There is a reason why X to W points in the other way, and that is because what really happens is for every point on the argument X, it came from something in W. So the order of the function should actually go in the direction of that function should go in the other direction. And then you do what's known as a pullback operation to, along that function, pull back the data on the circle onto the cylinder. So this gives us a very generic looking diagram, which we call the integral transform. There are other ways to call it, like polynomial spans. And this is a very interesting diagram in the set category, where these W, X, Y, and Z can be any finite sets. Like we looked at a concrete case of circle and a line and mapping back onto the line, passing through a cylinder, which is computed as the product of two broadcasted cylinders. But you know, they can be any four finite sets that you care about. It's a very generic diagram. This is the power of the categorical approach. We don't have to peek inside the objects to utilize the power of the diagram. You can think of these X, Y, Z, and W in the context of deep learning as just basically shapes of tensors, or in the context of functional programming, they could be types of data. And yes, great point, Federico. I think Andrew can maybe write the comment on this, that this is basically very related to certain kinds of Fourier transforms. Oh, and yeah, the sets don't necessarily need to be finite, but whenever we're doing deep learning, we're kind of assuming that it's supported only over a finite amount of points, because we discretize the domain. And once we have a diagram like this, we can then turn it into a transformation of actual tensors. So whenever I write these angle brackets WR, it means, you know, we have a tensor of shape W, and for every point on that tensor shape, we map to some data R, for example, k-dimensional vectors for something that would be in the middle of a neural network's features. Okay, so now we can then take this concept and now go back, reintroduce the graphs in the picture. Well, actually, before reintroducing graphs, I just want to say that this idea of the integral transform, and we show this in our paper, is quite powerful in that it also lets us, for the right choices of these four finite sets, rediscover many classical procedures that rely on message passing. So for those of you who have a theoretical computer science background, or if you worked with you know, these kinds of if you worked with these kinds of pathfinding algorithms like Bellman-Ford or Dijkstra or something, it turns out that for the right choices of these four sets, using the set of nodes V and set of edges E of a graph, you can actually rederive exactly the equations of these pathfinding algorithms. I don't have enough time to go into details of this, but if you read through our paper, we provide a very direct derivation that shows how you can take a diagram like the one on the right and recover the equation like the one on the left, which allows you to do pathfinding in general directed weighted graphs. So shortest pathfinding, to be precise. Okay, so now how does this work in the context of, say, a graph neural network? So as we said, we have a bunch of nodes in a graph, and this node B wants to receive a bunch of messages from its neighbors. So in this particular case, the sets W and Z are both the set of nodes. Like we're sending from nodes that are senders to nodes that are receivers. And in the context of a typical graph neural network, all senders also receive and vice versa. So we can set both of these two sets, W and Z, to be equal to B. So our first operation, the pullback arrow, and you see here I'm highlighting the different arrows inside our diagram to illustrate what's happening. We first, as we said, in the case of the cylinders, we have to first lift our data that lives on the sender objects to a space where we can apply a function on them to move them into the carrier object for the message. And in the case of graphs, very obviously, the edges will be the carriers of the message. So let's say I only have node features at my disposal. The arguments for my message function will be some features that come from the first node and some features that come from the second node. So our first arrow lifts data that lives on the nodes to two different pieces of data that live on the edge, right? Data of edge 0 gives me the sender node features. Data of edge 1 gives me the receiver node features. Once I have all of my arguments, I can then combine them together to compute edge messages that are going to be sent. And this is the argument push forward, the second arrow in our diagram. So here, what we're really doing is we're just taking these two arguments and combining them to compute a message function, G. And this now gives me features inside every single edge of my graph. And finally, once I've computed all of my edge messages, I can now send them to the receiver node to be aggregated. And this gives us the final step of the diagram, mapping us from the set of edges by integrating. So note in this case, we're summing over all the sender nodes. So we're basically doing an integral in a discrete space. So we're integrating over all of our neighbors to get the resulting updated node features. Once again, this can be generalized. This can be much more in-depth analyzed, and we do offer such an analysis inside our paper. But hopefully this gives a nice visual explanation for how we can explain the equations of a graph neural network. You know, for those of you who have worked with graph neural networks, hopefully this data flow should feel very familiar. And I hope it's a good way to start rethinking how data passes on a graph neural network, so that then we can use the same kinds of principles to analyze how data passes, say, within an algorithm or between circles, lines, and cylinders. And now, what have we been able to do with this? Because our paper doesn't just have theory. This is another thing which I find really interesting, is that, you know, it's a category theory oriented paper, but it actually proposes experiments, and we have proposed architectures that arise as a result of this analysis. So we didn't just explain what graph neural networks can do based on this. We actually used it to build something like a type checker for graph neural networks. Okay, so Ewan asked, could we go over what W, X, Y, and Z represent? And I am happy to oblige that. So basically, let's go back to the cylinder example. So the story is, I want to pass data from W to Z. And in order to do that, I must first materialize data on some message space. That's the Y. So in the case of graphs, we have one node sending to another node, and the carrier object is the edge connecting them. In the case of circles and lines, we have data on a circle and a line, and the message space carrying the messages is the cylinder, which is the product of those two. And in order to compute the messages, we need a collection of arguments for that message. And that turns out to be the element, the object X, which here is the broadcasted versions of the circle and the line onto those cylinders. Okay, so let's just go back to here. So let's try to get, you know, we looked at things abstractly and using pictures. Now let's try to look at some actual code, or well, pseudocode. So here on the left, I show how one might typically implement a graph neural network using the concepts in this diagram. Note here, I am deliberately dropping the set of edges from discussion just to keep things simple. I'm replacing the set of edges with V times V, so the pairs of nodes. So I'm basically assuming a fully connected graph in GNN terms. And basically, you can see here, I color-coded the operations of my graph neural network pseudocode to match the arrows in the diagram. So what do we do first? In order to send messages from nodes V to receiver nodes, which are also in V, I need first to compute the messages. So I need to have arguments for a message function, and I can obtain them by broadcasting my node data onto the edges. So I can obtain that since I'm assuming a fully connected graph, I can just tile my matrix X on axis 0 or axis 1. Here, tile is literally like the NumPy operation, you know? So it lifts me from something which is of the shape n to the r to the n times k, where it's like number of nodes times the number of features, to 2 argument matrices that are of the shape n times k. So for every edge in my graph, I have a k-dimensional vector coming from the sender and coming from the receiver, right? Now, of course, this is super wasteful from a memory perspective. I just wrote it this way to illustrate the concepts, right? If you were really implementing a GNN, you would have done it more efficiently than this. Okay. Once I've done that part, that's the first arrow, the pullback arrow, then we can compute the message function by just running our message mechanism psi over the argument coming from the sender and the argument coming from the receiver. And this now gives me the message objects, which are just 1 vector per edge. So it's n times m. And finally, once I have all of my carrier objects, as we said in the integral transform, we just integrate over all of the sender nodes, where you have this, general permutation equivariant aggregator O+. So this can be summing, averaging, maximizing, whatever it is that you need to do for the specific problem you care about, over all of your messages to get updated features in a particular node. So this is a graph neural network, a typical implementation of a graph neural network, and we've explained every step of it using the steps of the diagram. Okay. Now, why might this come in handy? Well, sometimes we don't just care about producing things in the nodes. We might also be interested in producing outcomes in the edges. So there are some tasks where edge representations are also required. And from my understanding, most of these expressive GNN papers, including DeepMind's GraphNets paper, the way in which it resolves this particular issue is by just returning the matrix of messages as the output edge features. So basically, it's the same diagram as before. If you look at the diagrams, so it's V to 2V squared to V squared to V. The only difference is that now you return V plus V squared. So you return something in the nodes, which is aggregated. And you also return the edge messages as edge outputs, right? However, if you're attentively eyed and looking at this diagram, as I told you, these are all finite sets, and this should be a diagram in the set category. Well, that actually doesn't work anymore. It breaks the categorical assumptions of the set category, because even though this is the preferred way to get edge output features in almost all graph neural networks in use today, it's not correct from a categorical perspective. The output morphism O that maps V squared to V plus V squared is no longer a function. It's now a relation, okay? Because this edge message vector in V squared needs to go to 2 different places. It needs to be reduced for the nodes, and it needs to be fed back as output of edges. Of course, this is now still a valid diagram in the category of relations, and clearly you can still implement it, like most implementations do this. But it still implies a form of what we call type checker failure, because the representations in V squared, you're taking them and you're reusing them for 2 completely different purposes, right? You're having to reduce them using the integration to get something in the nodes, and you have to reuse them to get something in the edges. And if the tasks required of the node and edge representations are very different, you're reusing the same representations for 2 very different purposes, and therefore you're placing representational pressure on them. So we might want to try to relieve that pressure. And in the specific instantiation of our paper, we looked at some of these edge-centric algorithms, and we saw that it might actually make sense to create this additional object, the cubic object, which looks at triplets of nodes at once. So now we compute messages not only over the edges, but also messages over, oh yeah, the plus here is a disjoint union operation. So basically, you now have messages computed not only over your edges, but also over triplets of nodes. For those of you who have seen some papers on expressive graph neural networks, like papers from Christopher Morris on 234 GNNs and stuff like that, the idea of computing features over triplets or generally over substructures of a graph shouldn't come as a very strange concept. But here we basically apply this idea that the type checker has failed, and now we compute two different message carrier objects, one v squared and one v cubed, and we reduce the edge messages to node features as before, but then we reduce the triplet messages to edge features. And now we've patched this diagram. We also need to obviously change the size of our argument set to properly match the arguments inside these particular messages. But now we have these two different kinds of messages, and they're used for two different purposes. So everything type checks again. We're not sending the same representation to two different places, and this might actually work. And actually, if you look at the downstream experimental results, this significantly improves performance on a standard algorithmic reasoning benchmark like CLRS. And that improvement is much more significant over algorithms that are edge-centric than all other algorithms in CLRS. So clearly, this kind of thing also leads to empirical gains rather than just being theoretical. So there was a question from Dobrik on, is there a way to fix message passing without making the complexity cubic? Yes, it is possible to fix it. So another possibility is to replace the v squared plus v cubed with 2v squared. So what this means is you're learning two different message functions, one to be reduced for the nodes and one to be returned as edge features. However, in the specific case of algorithmic reasoning, we found it very beneficial to compute cubic space messages, and there are some ways to sparsify that. We're looking into this, but basically, it just proved to be a better aligned choice for the algorithmic tasks that we were looking at. But you can also fix this problem by doing v squared plus v squared in the message space, and that wouldn't give you cubic space messages. Okay, so this is just, the overarching idea of the paper. Oh, I see there's a question on who was the author mentioned in the expressive GNN comment. That is Christopher Morris. Yeah. So, and there's a question on, could this improvement have come from more parameters of v cubed? We have actually controlled for the number of parameters in our experiments. So it did not come from this. Actually, the v cubed computes a very lightweight, I think even linear function of all the arguments. So we're trying really hard not to put like huge representational power from that particular thing. So we've shown just on a high level how we can use these concepts to define something that helps us check if our representations are not used for two potentially contentious purposes. And yeah, Umar asked, couldn't we argue that computing two representation of edges just amounts to doubling the channels and disallowing interactions? That is true. That's basically what it amounts to. But categorically, it means your representations are not used for two different purposes from the same source. And as a result, they might have a better time learning these interactions without representational pressure. Okay, so let's add a few concluding remarks, and then we might have maybe 10 minutes or so left for questions, which is roughly how much I was expecting given the scope of this massive lecture. Basically, I think I've been talking almost nonstop. I hope this was comprehensive. I'm very happy to, comprehensible. I very much hope to get any and all feedback you might have on Zoom or Zulip or otherwise. So we made it. So just as a recap, here's what I wanted us to cover at the beginning. Some interspersed philosophy on why is it a good idea to study category theory, now grounded in concrete examples. understanding the key concepts we're going to manipulate: categories, objects, morphisms, and functors. A bit of a mini tutorial to hopefully get your muscles developed on manipulating these objects, and then jumping right into one application of how we can ground deep learning, the context of message passing, in these concepts. So we've categorified the message passing primitive or some aspects of it using the idea of morphisms of finite sets. And then we use this to build this sort of mini type checker for graph neural nets, and built it using these ideas. And this, in a nutshell, is what we managed to publish in NeurIPS this year. As I said, I hope to see many of you at NeurIPS if you're coming, and discuss these ideas in person at the poster. But for now, if you have any feedback on this lecture or how well these aims were achieved, it's very much welcome and appreciated. It's literally my first time teaching these concepts in this particular way. And please use Zulip to follow up on anything which was unclear, or request more materials, or basically anything that's unclear after this lecture, because this is really going to be kind of the foundational content for the more in-depth explorations that will be delivered by Bruno, by Pim, and by Andrew in the coming weeks, as well as our guest lectures. And yeah, that was actually my last slide. Thank you very much for listening. Thank you for so many of you for sticking with me all the way to the end, and for having so many insightful questions and comments throughout. I tried to answer as much of them as I could. I saw Pim was also very active answering quite a few of them, and even the community was active in answering a few of them. So thank you all so much for listening. If you have any additional questions, I'll be around on Zulip. You can send me an email or anything you like. And yeah, let's maybe take the remaining 9 minutes and go through any questions you might have. Pim, I believe you're going to be moderating this part.
Yes. Hey, everyone. Please send your questions to the Q&A. Oh yes, as a administrative thing, I'll export the Q&A and post it on Zulip after this session. So regarding questions, a lot are popping up now. So Jules, for example, asks, can you tell more about the CLRS algorithmic reasoning benchmark, if time permits? So you tested your paper.
Yeah, that's a great question. We can drop a link in the Zulip, or if I don't have a computer handy, but if any of the organizers or someone else who knows about CLRS can copy paste the link to that paper, that would be good for Jules. But what I will say is that CLRS is just a collection of tasks of algorithmic reasoning. So learning how to execute individual steps of classical algorithms, so that we can benchmark to what extent can our graph neural networks or other machine learning models imitate those reasoning steps of classical algorithms out of distribution. So it's basically a very good test bed. It was a very good test bed for how good of a reasoner our models actually are. And that's why we use it in this particular paper, to just test the reasoning capabilities of the various GNN benchmarks we proposed. But beyond that, there exist many other papers, like the paper from Christopher Morris that I mentioned, which showed that generally computing triplet representations in GNNs seems to be a good idea for expressive power.
Yeah, thanks. The next question, can you recommend some more basic sources on message passing in general?
Yeah, so one thing I would suggest, obviously here I said it in passing, but if I can self-promote, I basically, I gave this 1-hour lecture on graph representation learning, which is on my YouTube channel. So if you search for theoretical foundations of graph neural networks from myself as the speaker, you will find basically a 1-hour deep dive that starts from the basics of permutation symmetry, how from them we get the message passing primitive, and then all the various ways in which they have been rederived and reused and stuff like that. So I would recommend watching that talk as a basic source if you're interested in talks. If you want to read something maybe a bit more in-depth, there exists a fantastic book from Will Hamilton on graph representation learning, which introduces graph representation learning in a much more longer scope manner over many book chapters.
Thanks. I think Matthew Pugh would like an answer to the question you asked. What is the co-exponential objective set?
I think that's an answer we should arrive at together through Zulip discussions. So I will question unanswered for now.
Sounds good. A very interesting question from Jeffrey Nickerson. Is there a categorical way of thinking about random walks in the context of graph neural networks?
That is a very good question. I haven't thought about it too much, but what we can think about as a sort of random walk is like we can imagine random walks as a sort of message passing mechanism where we have slightly more, I guess, stochastic interactions between the various nodes that we have. And yeah, like you can have a biased random walk interpreted as a sort of weighted adjacency matrix. And well, I don't want to jump too much into these things, but in lecture 4, Pim will tell you all about how we can turn adjacency matrices into these groupoid structures and then use them to define a more interesting form of graph neural network using them. So you can use similar ideas, I think, to rediscover random walks as sort of, you know, adjacency matrices with like weighted coefficients. Yeah.
Yes. Frank Albinet is asking if you are releasing any source code or notebook with your paper because they like to play around with it.
Yeah, actually we have, so it's actually interesting. So we have the CLRS benchmark, which is publicly released on GitHub, on DeepMind's GitHub page. So it's github.com/deepmind/CLRS. And we recently used these triplet representations from this paper to significantly improve both our single task and multitask performances across CLRS. You might have seen on the archive, we have this new paper, a generalist neural algorithmic learner, which we released a few weeks ago. And we actually recently put all the code corresponding to that paper, including the triplet representations from this dynamic programming paper, in that same code base. So if you go to GitHub DeepMind CLRS and check some of the latest commits in that repository, you will see exactly the codes for the various GNNs with and without triplet representations. Yeah.
The next question I find is a general question: how applicable is category theory for learning from high-dimensional data, say text and images?
Right. So that's also a very interesting question. I would say it is quite applicable if you are careful with how you use it, right? So naively applying a categorical concept, and I think, Pim, you'll give a very direct example of this in a few weeks' time, but basically, if you directly apply a categorical rule on a very complicated domain like a big graph, yes, you will end up with an architecture that you cannot feasibly actually implement because the number of parameters will blow up or it won't generalize outside of the training set or something like that. But the idea here is, you know, we see category theory not always as a tool that directly tells you how to implement, but something that you can use as inspiration or as perspective to then define a more local or elegant version of the rules that will actually be scalable and respect the categorical rules that we care about. So this, you know, the local natural graph networks is one example of this, which is a scalable graph neural network layer that actually is more expressive than what, say, the simple geometric equivariant representation of GNNs would imply. So definitely it is possible to apply it to high dimensional data over big domains. You just have to be careful about how you enforce the constraints that come out as a result of it.
I have a question on neural assembly calculus via the framework of category theory. I don't know if you've heard of it. I haven't.
Yeah, me neither, but I would be very interested to take a look at it. It sounds, based on the name neural assembly calculus, it sounds like it would be a good fit for categorical reasoning, but yeah.
I'll comment myself on Umar Kaba asking about the relationship between this, what you presented here, and Hagen Ron's work on equivariant maps and graphs. I'll comment on that in lecture 4. I think that would be less appropriate. So should we do a final question? Yeah, maybe you want to comment on the last question that just came in. Are there any works that look into disentanglement of representations in deep neural networks from a category theory perspective?
I'm actually unaware of any papers like that, but for me, like disentangled representations can be to some extent coupled with trying to understand some kind of causal structure behind the generative factors of your data. So I would imagine maybe Taco's guest lecture can give a bit of insight into that when it happens. But yeah, I'm not aware of anything that like explicitly tackles disentanglement from this perspective. Yeah. I think this could be a good place to stop. But these were like really fantastic questions. Thank you all so much.
Will you put the slides already available?
The slides are already on Zulip, actually. So yeah.
All right, thanks everyone. Thanks, Petar, for the fantastic talk. We had a lot of very positive replies in the Q&A to your talk. So I think it was a success.
Thank you all so much, and thanks, Pim, for moderating it. It was a bit challenging to present this for the first time, but we pulled through. I really found it exciting. Thank you all. I hope